So good evening, everyone. Last presentation, so please stay awake with me. My name is Renata Latypova, and I'm a postdoctoral researcher from University of Oulu, Finland. And today I'm going to talk about the effects of low temperature tempering, hydrogen diffusion, and trapping in direct quenched martensitic steel. This is still an ongoing study, and we did it in collaboration with Ghent University, where I spent 7 months for my research visit. The content of my presentation will be the following. So I have the background, test materials. I'll talk about the microstructure and the mechanical properties of the materials. I'll introduce the testing methods. And then as last part, I have results and summary. Let's start with the background. Low temperature tempering is a common heat treatment for martensitic ultra high strength steels, which is typically used to improve their mechanical properties. Low temperature temper has also been reported to improve hydrogen embrittlement resistance of ultra high strength steels. However, depending on the tempering temperature, we might have opposite effects on hydrogen trapping and diffusion. So if we start with temperature from 25 to 100 degrees, we have, for example, carbon segregation to dislocation, formation of quadrilateral atmospheres, which then will reduce trapping sites for hydrogen. Then if we go about 100, so 100 to 200, we might have formation of transition carbides. Of course, that depends on the alloying. And that will then increase the trapping of hydrogen. And as last part, we have transformation of retained austenite. So then again, we have less trapping sites of hydrogen. As for the test materials, we have the original direct quenched steel from the steel company, which has an auto-tempered lath martensitic microstructure. We tempered this direct quenched steel at 50 degrees, 150, and 250 with 1 hour holding time. This was specifically done so that we can see all these different effects. So we have carbon segregation with 50 degrees, then again, carbon segregation with 150, and the possible formation of transition carbides. But spoiler alert, we didn't find them, but we still keep looking at TM. And with 250, we have the transformation of retained austenite. As for the mechanical properties, well, this is ultra high strength steel. So with tempering, we did observe a slight increase in the yield strength and decrease in the hardness properties. Here are some images of the microstructure. Like I said, we have lath martensitic steel, but we also have some amount of cementite because this is an auto-tempered microstructure. Unfortunately, we cannot detect the cementite with XRD, but we can do etching to reveal the cementite. And as for the pry-austenite grain structure, this is just nice to know information. We have this pancake-like pry-austenite grains. So this is definitely something we need to consider when we do mechanical testing with hydrogen. A little more about the cementite. So we have, like I said, we couldn't measure it with XRD, but we could use thermocalc for calculation of the fractions and also image analysis. And based on the thermocalc calculation, we could see that cementite fraction should be increasing with the elevated temperature, so with the 250 tempering. As well, we could see the same result with the image analysis, but I would still consider thermocalc more reliable in this case. As for the retained austenite, we did DSC and XRD. And with DSC, we can see a peak for the composition of retained austenite for all of the materials except for the 250 tempered, which means that with that high temperature tempering, we already lost the retained austenite. Same for the XRD, we could see the retained austenite peak for DQ and the 150 tempered, but not for 250. So with 250, we definitely don't have retained austenite. As for the testing methods, we utilized a permeation technique, first in Oulu. For this, we used palladium coating on the detection site, and we used successive transient method for calculation of diffusion coefficients. Then we did permeation with and without loading in Ghent. For those, we did not use coatings because we're utilizing loads. And there we used from 50 to 100% from the yield strength. Then we also were interested, of course, in the hydrogen concentration in the trapping site. So we did melt extraction and TDS. And as last part, we have preliminary results from the tuning for testing, which is a testing method developed at Oulu University. Basically, we have a tuning for chip samples with a notch, which we stress with the load cell clamping system. And then we look at the loads and we can determine the initiation, propagation, and final fracture of the sample. So just in order, first we have hydrogen diffusion, then we're going to focus on hydrogen trapping, and then a bit of mechanical testing. So now the results. On the left side, you can see the results from Ghent, where we did not utilize coating. As you can see, the diffusion of hydrogen in direct quenched steel is slower than in the 250 tempered. Same result we obtained also in Oulu with slightly different technique. So first we have direct quenched steel, which has the slowest diffusion. After that, we have increase for 50 tempered, 150 tempered, and then the biggest increase for the 250 tempered. So we have two slightly different techniques, but we get the same trend in both cases. And this was expected because with the tempering, we do reduce the trapping site because carbon will occupy some of the dislocations. The surprising results came after we added the loading. So on the left side, you can see the direct quenched steel, and the assumption was that if we're going to load the samples, we're going to have faster diffusion. As you can see, this wasn't the case. With direct quenched steel, we saw a slight decrease in diffusion coefficient with 50% loading, and also with 75 to 100%. We thought that perhaps this could be the retained austenite because we do have a small fraction of it, and we have seen that this can actually happen under loading for other materials. And then we tested the 250 tempered, which definitely doesn't have retained austenite. And we could see exactly the same thing. So this was very surprising because definitely not retained austenite is causing this slower diffusion. But with 250, we also see the decrease, plus it was even more than for the direct quenched. Obviously, we were interested what kind of trapping sites might be active at this point. And we did TDS to see, okay, maybe we have additional peaks for trapping. Unfortunately, we did not see any peaks, so no strong trapping involved. This indicates that the diffusion is getting slower because of the weak trapping in these materials. Potential trapping site in this case could be the cementite interface, which is being activated under load. And this would make sense because with 250, we have also higher fraction of cementite, which would explain why decreasing more than DQ. And perhaps there could be also a competition between carbon and hydrogen dislocation, which could lead to additional trapping under load. Now the hydrogen concentration. First, we did melt extractions, and this was done to determine the saturation time for the samples. 3 hours was an appropriate one in this electrolyte in this condition. And here we also could see that with the direct quenched steel, we have the highest concentration of hydrogen, and then it slowly drops or decreases for the tempered ones, meaning that most likely dislocation are occupied by carbon, and therefore we have less trapping sites for hydrogen. Same thing we could see with the TDS. We saw the slight decrease for the hydrogen concentration, but of course we were also interested in the trapping sites. And all the data that we got from TDS, we never saw strong trapping, so no high temperature peaks. We only had one peak for the lower temperatures. So this means that retained austenite is not trapping hydrogen in this case, so it's not being activated without load or with load. And assuming in these materials that what are the potential trapping sites? So we have grain boundaries, and then we have dislocation, this is for sure. And for the DQ, T50 and T150, we deconvoluted the peaks, and we could see that the first peak could be the dislocations, and then the second one, the grain boundaries, which could be in line with the literature and the observed activation energies for them. However, with the high temperature tempering, we were struggling with the peaks because for this material, 1 peak, 2 peaks, we always got very, very high activation energy, which is not possible with these temperatures. Therefore, we had to add a third peak, which goes in the middle of the curve. And this peak could potentially be cementite trapping. So main conclusion is that we have less hydrogen with the 250 tempered, but the trapping can be different in this material. So we might have cementite active there. And now for the mechanical testing, we really have just preliminary results because this is still an ongoing study. We did this incremental step loading for our materials. So basically we started with 25% stress from tensile strength, and then we increased it by 5% hourly. And currently we have results for all of the materials, but direct quench and the T50, T150 are slightly overlapping, but we could definitely see the increase for the 250 tempered. So it does seem like low temperature tempering at that temperature can actually slightly improve hydrogen embryoma resistance. But of course, there is a lot more questions. For example, the cracking mechanisms. So we're going to continue with investigation of the fracture surfaces, maybe do interrupted testing, and then also check the crack tips. And as the last slide, I have the summary. So make conclusions from this study. Well, we could see that cultural atmospheres reduce hydrogen trapping at dislocations, and we have proof from melt extraction and DDS. And with sufficient tempering temperature, the 251, it could lead to additional trapping by cementite since we also increase the fraction of it. Hydrogen diffusion slows down with increasing tensile load. And the reason for it might be the activation of cementite interfaces and also the competition between carbon and hydrogen at dislocation. This is interesting from the real life perspective because if we test these two materials without the loading, we can see a big difference. I mean, one material has faster diffusion than the other, but then if we apply the load and the higher we go, the closer they get together. So actually there is no big difference there. And I think this is one of the reasons why it's important to do testing also on the load. And as last conclusion, we have that so far we can see slight improvement with the 250 tempering in terms of hydrogen embryoma stability. But like I said, still ongoing studies. So we're going to look into the cracking mechanism and report later on this matter. Thank you for your attention. And do you have questions?